All right, so the first couple of problems I'm going to do will be concerned with computing something that we call a difference quotient. So first, let me define what a difference quotient is. So if we have a function f of x, then the difference quotient is defined to be this expression. It's f of x plus h minus f of x, and then all over h. Okay. So maybe just a quick survey. How many of you have seen this expression before? Does this look familiar to any of you? Okay. And then maybe before I continue, I guess it's worth kind of gauging what my audience is like. So like I said, this is a pre-cal review. Have any of you by chance already taken calculus? Like maybe in high school or something like that? Okay, all right. Yeah, okay. So for those of you who did take calculus, you'll recognize the difference quotient is involved in the limit definition of a derivative, okay? And for those of you who are not in calculus, you'll learn about derivatives later this semester. And when you learn about derivatives, you'll see the difference quotient come up in the definition, okay? And so I'm just going to do a couple of examples of computing difference quotients right now. Okay. And so for the first example, let's look at a polynomial function. Okay. So you've got this function here, f of x is x squared plus 5x minus 3. And I'm going to calculate the difference quotient, and I'm going to simplify it a little bit, okay? So in order to calculate the difference quotient, one of the things that we need is f of x plus h. Okay. So in order to get f of x plus h, to evaluate this, what you do is you replace each x with an x plus h in the formula here. So if f of x was x squared plus 5x minus 3, f of x plus h would be x plus h squared, and then plus 5 times x plus h, and then minus 3, okay? And it's probably worth kind of simplifying this a little bit. So I'm going to go ahead and just kind of multiply everything out. So x plus h squared is x squared plus 2xh plus h squared. Okay. And then likewise, I'm going to go ahead and distribute the 5 into the parentheses. So that'll give us 5x plus 5h. And then we've got that minus 3 at the end, okay? Does everyone understand how I did that multiplication? All right, cool. Okay, so then let's go ahead and form the difference quotient. So we're going to take what we found for f of x plus h. We're going to minus f of x and divide by h. And let's see what this looks like. So first, I'm just going to plug in everything that we calculated for f of x plus h. Okay. All right, and then we need to minus f of x. Now, f of x was x squared plus 5x minus 3. Notice that I'm being a little bit careful. So if I want to minus f of x, I want to minus this whole expression. So I put a parentheses around it just to emphasize that I'm going to minus the whole thing, okay? And then this is all over h. Okay. So in the numerator, what we'll do is we'll go ahead and distribute this minus sign into the parentheses. Okay. So if we do that, that will give us minus x squared minus 5x and then plus 3, okay? Okay, so let's ignore that now. Okay. All right. And then at this point, I want to simplify a little bit. So when you're calculating difference quotients, you'll always be able to simplify a bit. To start with, in the numerator, we have an x squared minus x squared. We also have this 5x minus 5x. And then we have minus 3 and plus 3. So all of those are going to cancel out first. Okay. So let me just rewrite what we have right now. So we have in the numerator, we still have 2xh plus h squared, and then plus 5h. And then all of that is divided by h. Okay. All right, now when you're calculating difference quotients, something that you should be able to do is this h in the denominator, you should always be able to cancel it out at some point, okay? And usually that's something that you want to do when you're simplifying. So in this case, if I want to cancel out the h in the denominator, what I can do is in the numerator, every term has an h. So I can factor the h out. So one h from every term gets factored out. And then after I do that, I can now cancel out this h in the numerator with this h in the denominator, okay? So then that leaves me with 2x plus h plus 5 as the difference quotient, okay? I think that's good enough. Okay, so then in your calculus classes, so after you calculate the difference quotient, you would do like a little bit more in order to find the derivative, but since I don't want to get to derivatives today, since we're just doing a pre-cal review, I'll stop it here, but in your calculus class, you would do just a little bit more after this point, okay? All right, so I'll do just 2 more examples of calculating difference quotients with like different types of functions. So in the first example, we had a polynomial function. So let's try a different type of function now. So let's say f of x will be square root of 3x minus 7. Okay. All right, so same type of question. We're just going to calculate the difference quotient. Okay, so first I'll just calculate f of x plus h. So all we do is replace x with x plus h in the original formula, and that gets us f of x plus h. Okay. And it's probably useful, I think, to distribute the 3 into the parentheses. So I'll go ahead and do it now, although you could do it later as well, so that's not like a big deal. But I just feel like I'll go ahead and do it now. Okay. All right, so now let's form the difference quotient. So f of x plus h minus f of x all over h. Okay, so we have, this is f of x plus h. And then we have minus, and then f of x. Okay. All right. Okay, now remember what I said earlier in the first example. Usually when you're calculating the difference quotients, you want to somehow simplify the expression to a point where you can cancel out the h's, or at least cancel out the h in the denominator somehow, okay? So over here right now, it's maybe difficult to see what you could do because you can't really like combine these two square roots in the numerator. So in order to cancel out the h in the denominator, there's sort of a trick that we use. Okay. So the trick that we're going to use is we're going to multiply the numerator and the denominator by the, in this case, by the conjugate of the numerator. So let me, as a brief aside, just talk about like, what do I mean by the conjugate? So these two expressions, like a minus b, a plus b, these are called conjugates. At least in your calculus class, we call them conjugates. So like a minus b is the conjugate of a plus b, and a plus b is the conjugate of a minus b, okay? And what's useful for us is when you multiply two conjugates together, so if I do a minus b times a plus b, if you were to like FOIL all of this out, you'll find that the product is equal to a squared minus b squared. So in the numerator over here, if I think of this square root as a and then this square root as b, then I have like an a minus b type of expression there. So what I'm going to do is I'm going to multiply by the conjugate a plus b. Okay. And the idea of doing this is, so here my a and my b each have a square root in them. But when I multiply by the conjugates, since my a and my b get squared, that means that the square roots are going to go away, okay? So the hope is once you get rid of the square roots, you'll be able to maybe combine some terms and then simplify from there, okay? Now you can't just multiply the numerator by this expression because that would just change the whole problem if you do that. So in order to maintain the equality on both sides of the equation here, I need to multiply both the numerator and the denominator by the same thing. Okay. All right. All right, so then when we multiply these two fractions together, so remember multiplying fractions, you multiply the numerators together and then you multiply the denominators together. So in the denominator, we just have h times this, and I'm just going to write it as h and then times in parentheses all of this. Okay. Some of you might have thought to distribute the h to each term when you multiply them, but it's going to be better to leave the h on the outside because remember that we're actually trying to cancel out this h. So for the purpose of trying to cancel it out at some point, it's better to leave it outside. Okay. Now in the numerator, we're multiplying a minus b times a plus b. So the result of multiplying those together should be a squared minus b squared. Okay. So if a was the square root of 3x plus 3h minus 7, then a squared would just be 3x plus 3h minus 7. So the square would just get rid of the square root for us. And then likewise, b squared, the square would just get rid of the square root. So it's really just 3x minus 7. But be careful, you're subtracting all of this. So we should put parentheses around that to indicate as such, okay? All right. So by multiplying by conjugates, we got rid of the square roots in the numerator, and now we can try to combine like terms here, okay? Okay, so in the numerator, if we were to distribute this minus sign into the parentheses, we would get minus 3x and then plus 7. So I'll distribute that minus sign. Okay, and then from here, in the numerator, 3x's, okay, we'll cancel 3x minus 3x. And then we also have minus 7 and plus 7 will cancel, okay? So that leaves us with just the 3h in the numerator. And then we have the same denominator still. And at this point, we can now cancel out the h in the denominator with this h in the numerator, okay? So finally, what we end with is 1 over the square root of 3x plus 3h minus 7 and plus square root of 3x minus 7. Okay. And then this is good enough for us. So the main thing that we're trying to do when calculating difference quotients is to cancel out the h's. And so now that we've done that, this is a good enough place to stop, okay? All right, any questions about that? Okay. So then finally, I'll just do one more difference quotient example. Again, doing like a different type of function. So we had a polynomial function, we had a square root function. Okay, so now let's consider this function here. Okay. So it's 2x over x minus 6. This type of function is called a rational function, by the way. So just like some terminology. Okay. And so in general, a rational function just refers to a function of the form like a polynomial over another polynomial. So any function of that sort is usually called a rational function. Okay. Okay. All right, so again, I'm just going to calculate the difference quotient. So to start with, let's look at what f of x plus h would be. So I'm just going to replace each x in the original formula with an x plus h. Okay. And I think I'll maybe go ahead and distribute the 2 into the parentheses here. So we'll get 2x plus 2h over x plus h minus 6. Okay. Okay, and then we'll use that to form the difference quotient. Okay. Okay, so this is going to be a little bit messy. So f of x plus h is, let me write that down. This is f of x plus h. We're going to do minus f of x. And then all of this is divided by h, okay? Okay, now we want to simplify this somehow. And again, at some point we want to try to cancel out the h in the denominator. So the only thing that we can kind of do in the numerator is we can maybe try to combine the two fractions together, okay? So in order to combine the two fractions though, so we're subtracting them. When you're adding or subtracting fractions, remember that you need a common denominator in order to combine them, okay? So let's first get a common denominator between the two of them. Okay. So in order to get a common denominator, let's take the first fraction here, and we'll multiply the top and the bottom by the x minus 6. Okay. So that way we pick up an x minus 6 in this denominator. And then for this fraction here, we'll multiply the top and the bottom by x plus h minus 6. Okay. So then that way, both of the fractions will now have the same denominator, x minus 6 times x plus h minus 6, okay? Okay. I'll also do maybe one other thing to sort of simplify the problem. So we're going to try to combine these two fractions together. I'm also going to do something else. So, here we have like a fraction, a bunch of fractions, but then they're all inside of a bigger fraction, right? And so having a fraction inside of a fraction is not very pleasing to the eye. So I'm just going to rewrite the problem so that I don't have that anymore. And the way I'm just going to do that is we have everything here being divided by h. Dividing by h is the same as multiplying by the reciprocal 1 over h. So I'm just going to rewrite the problem so that instead of dividing everything by h, I'm rewriting it so that I'm multiplying everything by 1 over h instead, okay? And then for this step in the numerator, they're going to have a common denominator of x minus 6 times x plus h minus 6. Okay, so I'm going to put them all together. And in the numerator, we're going to have x minus 6 times 2x plus 2h. And then here we're going to have minus 2x times x plus h minus 6. Okay. And I didn't want to do too much in that step there, so I just copied it down first. Okay. Okay, but now what I'm going to do is I'm going to, multiply everything out in the numerator, and we're going to try to like cancel out some terms once we multiply everything out. Okay. Okay, so we're going to have to sort of like FOIL this. So we're going to get 2x squared plus 2xh minus 12x minus 12h. Okay. And over here, if we distribute the minus 2x, that'll give us minus 2x squared minus 2xh, and then plus 12x. Okay. Okay, now the numerator, you don't need to multiply this out though. I'm just going to copy it down then. The reason why we wanted to multiply out the numerator is because at some point we need to get an h in the numerator that will factor out with the h in the denominator. So to get to that point, we first wanted to multiply everything out, okay? So then once we multiply it out, some terms will cancel, 2x squared minus 2x squared, and then minus 12x plus 12x. I guess even these terms will cancel, 2xh and minus 2xh. Okay, cool. So that leaves us with 1 over h times negative 12h in the numerator. Over this product. And now that we simplified the numerator, we see that we can cancel out these h's. And then that will leave us with negative 12 over x minus 6 times x plus h minus 6. Okay. All right, any questions about that? Okay, all right. So hopefully you guys were comfortable with like all the algebra that we were doing there. Okay. So I'm gonna move on to like the next set of problems that I have prepared. Okay. So then pretty much for the rest of today, I'm going to be looking at different types of functions. So I'm going to start by looking at polynomials and then build up to more complicated types of functions from there. And we're just going to be analyzing some of the basic properties of those functions. And something else that we're going to be doing is we're going to be making sign charts for each of these functions. So a sign chart is just like a tool that we use to determine where a function is positive and where a function is negative. So those of you who have taken calculus before you'll be somewhat familiar with that. And then for those of you who maybe haven't taken calculus before, you maybe haven't seen this, or maybe you have, I'm not sure. But we'll do a bunch of examples of that, so you'll get tons of practice. Okay. And I'll reset my counter, I suppose. Okay. So like I said, I'm going to start off by looking at some polynomial functions first. And for the first example, we have the polynomial x squared minus 4x minus 21, okay? And so what I want to do in this example and most of the other examples that we have today, I'm going to have pretty much the same set of like instructions, if you will. So we'll talk about what the domain of each of the functions is. And then we're going to find where our function will be equal to 0. We'll find where our function is positive and also where our function is negative, okay? Okay, so then for polynomial functions, what's the domain of any polynomial function? You guys know what I mean by domain, I'm guessing? Yeah, go ahead and speak up or type in the chat. Okay. Yeah, so the domain of any polynomial function is all real numbers, right? So oftentimes when they ask for like the domain of a function, they'll want your answer in interval notation. So all real numbers as an interval, you would just say it's an open interval from minus infinity to infinity, okay? Okay. Now let's take a look at where this polynomial will be equal to 0. So I'm going to take the polynomial function. I'm going to set it equal to 0. Okay. And then we want to solve for x. So what's the strategy for solving for x in this equation? There's maybe more than one strategy, but what strategy would maybe come to your mind first? Yeah, factoring. So factoring is going to be an essential skill to have in your calculus class. So hopefully you guys are familiar with factoring. We'll be doing a lot of factoring today, okay? So in order to factor this polynomial, well, I mean, maybe you guys can tell me how this polynomial will factor. Yeah, very good. Yeah, okay, that's fine. Yeah, so x minus 7 and x plus 3. So minus 7 and plus 3 multiplied to be negative 21. They add to be negative 4. So that's how you figure out the two numbers that you need. So then from here, we see that there's two solutions to this equation. If x is equal to 7, or if x is equal to negative 3, Those are the two values of x that will make this equal to 0. Okay, that's good. So let me maybe say this is part A, part B. It doesn't matter, I guess. Part C, part D. Okay. So then we found the two places where our function is 0. So then for the last two parts, finding where the function is positive or negative, the way that we typically do that is we'll create a sign chart. Maybe like a sign table or whatever people call it. So what we do in the sign chart is, so I'm going to draw a number line. And for polynomial like this, I'm just going to mark down the two zeros that we found. So we have 1 0 at -3. We've got another 0 at +7. Okay. Now also, maybe like off to the side, let me draw like a little picture. So just for those of you who like haven't seen this before, I just want to give a quick explanation of like how this works. So if we were to draw a graph of this function, we know that the graph of this function is going to pass through these 2 points on the x-axis. Let me add the y-axis into the picture as well. Okay. So then these two zeros that we found, they divide the number line into 3 separate intervals, 1, 2, 3. Okay. And what's going to happen is in each of these intervals, our function has to be either always positive or it has to be always negative. Okay. And to get a sense of why that has to be the case, well, imagine if, let's say, in this interval out here, imagine if our function was not always positive or always negative. So meaning that at some point it was positive, but then it became negative. If this happened, then you can see in the picture we would have had another 0. But we know that there are no other zeros because we solved for them, and these were the only 2 zeros that we found. So your function can't switch sign in any of the 3 intervals, because if it does switch sign, that adds another 0, which we know is not possible. Okay? So the function is either always positive or always negative in each interval. So to determine where it's positive and where it's negative, we just need to pick like a test point in the 3 intervals that we have and plug that test point into our function to determine its sign in each of those intervals. Okay. So let's say in this interval to the left of -3, I'll pick a number to the left, let's say -4. Okay. And between -3 and 7, pick a number in between them. 0 is a nice number for that. And then we'll pick a number to the right of 7. Let's use 8. Okay. Okay, so we're going to plug these test points into our function. And usually at this point, when you're plugging your test points into your function, I think it's usually easier to use the factored form of the function for this. So I've rewritten f of x, but factored. So now let's plug in -4, 0, and 8. Okay. So first, plugging in -4, into here, you're going to get negative 11, so you're going to get a negative number. And then negative 4 plus 3 will be another negative number. So we have two negatives multiplied together. So the actual number itself is not too important. What we want to pay attention to is what is the sign of the function. Is it positive or negative? So at negative 4, our function was positive. So we can conclude that the function is going to be positive in this interval to the left of negative 3. Okay, so I'll put a plus sign up here now just to keep track of that. We plug in 0 for x. You're going to get a negative number times a positive number. So we know that altogether the function is negative at 0, so it's negative in the interval between negative 3 and 7. Finally, if we plug in 8 into the function, if x is 8, you can see that both of these are going to be positive now. So altogether, the function is positive at 8, and therefore it's positive in this last interval. Okay. And then with the sign charts that we had there, we can answer where is f positive and where is f negative. So here we see that f would have been positive in the interval negative infinity to negative 3. And it's also positive in this interval from 7 and then I guess out to infinity. So you can use a union symbol for this. So it's positive in this interval and also this one. So you can use a union symbol to denote that. I think some people would also accept if you just list the two intervals like that without a union sign. To me at least, both of these would seem acceptable as an answer. As for where the function is negative, here we saw it was negative only in the middle interval between negative 3 and 7. Okay. And then I'll make one more comment, which is, so if you're wondering why we're using like open intervals for this part, the reason is we know that at negative 3 and 7, the function was equal to 0. And so 0 is neither positive nor negative. So therefore, for these 2 points, they should be left out of these intervals, indicating where f is positive and negative. Okay. All right, so we'll do a couple more problems of this sort. Okay, so let's consider the function f of x. We'll do x to the 4th power plus 2x cubed minus 3x squared. Okay. And we'll have the same like set of instructions. So let me maybe scroll back up real quick. All right. All right, cool. Okay, and so this first part A, finding the domain, there's not much to it right now because we're just looking at polynomials. Yeah. But later on, when we look at more complicated functions, then we'll have to do some work to figure out what the domain is. But for now, it's just minus infinity to infinity, okay? Okay, now to check where f of x is equal to 0. So just as in the previous example, we want to factor this function. Okay. So if we were to try and factor this, it looks a little bit more complicated this time because you have like a higher power terms. What should we do if we wanted to factor this function? Yeah. So the first thing we would do is every term has an x squared in common. So we should factor out the x squared first. That will leave us with x squared plus 2x minus 3. Okay. And we're trying to figure out where is this equal to 0. So then once we factor out the x squared, we have this quadratic remaining, and then we can further factor it even more. Okay, so to factor this, it would be x minus 3 and, plus 3, right? And x minus 1. Okay. So they multiply to be negative 3. They add to be positive 2. Okay. All right, and then from here, we see this time that we had 3 zeros. So if x is equal to 0, that's one solution. If x is negative 3, that's another solution. And if x is positive 1, that's our third solution, okay? So then to figure out where the function is positive and negative, we're going to create our sign chart again. Okay. And we'll pick a test point in each interval. Okay. All right, and then we want to plug each of our test points into our function. And again, it's easier to use the factored formula for f. So I'll copy it down here so we can see it more easily. Okay. So then we'll plug in negative 4. Okay, so x squared, that's going to be positive, right? Negative 4 plus 3 is negative. And negative 4 minus 1 is also negative. So it's positive in the first interval. Okay. Let's plug in negative 1 next. So we plug in negative 1. Okay, that's always positive. That's going to be positive now, negative 1 plus 3. But negative 1 minus 1 is still negative. So now this is, f is negative on the second interval. If we plug in 1/2 for x, okay. Okay, so again, x squared will be positive. If you add 3, that will be positive. 1/2 minus 1 is still negative. Okay. So then this is going to be negative here. And then lastly, if we plug in 2 to the function, this time all 3 of these are going to be positive. So f will be positive in that last interval there, okay? All right, cool. So then here we see that f is positive in the interval from infinity to -3. And also in the interval here from 1 to infinity. And then it'll be negative in the interval from -3 to 0. And also in the interval from 0 to 1, okay? Now, I think a somewhat common question that I get would be, if you have something like this, why not just do -3 to 1? Why do we have to split it at 0, okay? So you don't want to include 0 as a place where f was negative, because instead, when x was 0, our function was 0, and that's not negative, okay? So the function is not negative when x is 0, therefore you should leave 0 out of the answer here. So that's why we have to split it into the 2 intervals like this. Okay. Any questions about that? Okay. Let's do another example. So the example 3. Okay. So let's see what's going on with this example. Again, we're still just working with polynomials, so don't have to worry about the domain at all. It's just going to be all real numbers. Okay. Okay, let's look at where this function was equal to 0. All right, so who can tell me how to factor this polynomial? Move 7 to the right, factor out x. Does anyone have another suggestion, maybe? Okay. Not every quadratic polynomial can be factored, right? So at least not factored easily, maybe. So if you come across a situation like this where if you try to think of 2 numbers that multiply to be 7 but add to be 4, you'll maybe find you can't really find any numbers like that. So in such a situation, remember that you can use the quadratic formula instead, okay? So I'll give a quick reminder on the quadratic formula. So whenever you have a quadratic equal to 0 and you're trying to solve for x, the quadratic formula just gives you a formula for what your two solutions are. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So most of the times in your calculus courses, your polynomials will work out nicely enough as to where you can factor them. But I wouldn't count out the possibility of needing to use the quadratic formula every once in a while. So just want to make sure that we remember it. Okay. So let's see what happens if we apply the quadratic formula to this problem. So b is 4, c is 7, a is 1. So we have negative b plus minus square root of b squared. So 4 squared is 16. Minus 4 times 1 times 7. So let's just make that 28. All over 2 times 1, so just over 2. So simplifying, that's negative 4 plus or minus the square root of negative 12 over 2. Okay, so what should I do next? So should I go ahead and make a sign chart with the two solutions that we found, or what's going on here? Okay, so maybe the reason why you guys aren't talking is because you notice that we have a negative number under the square root. And so can't square root a negative number unless you want to work with imaginary numbers, okay? So here what we're finding is that there's no, this is going to be complex, so we have no real solutions. To this equation. So what that means is there are no values of x for which our function will be equal to 0, okay? Okay. So then the answer to part B, in a sense, the answer to part B is that there is no answer to part B, okay? Okay, so then what does that mean for part C and part D? Well, normally what we did is we would make a sign chart, right? And what we would do in our sign chart is we would label our two zeros, or however many zeros we had on the number line, and then pick a test point in each interval that we had. Okay, but here we have no zeros to mark on the number line, right? So that means since we have no zeros, we only have one interval, which is the whole number line itself. So we just need to take one test point in this one interval that we have. So 0 is a nice number on our number line. Okay. So let's plug our test point into our function. And this was our function f, so if you plug in 0 for x, you see that f of 0 is 7, which is positive. So there was only one interval to look at, and we picked a test point in it. F was positive, so that means our function is positive on the whole number line, okay? All right, so that means f is positive for real numbers, actually. Okay. And then what does that say about where is f negative? Well, there are no places where f is negative, okay? So the answer to part C is that there is no answer, if you will. Okay. All right. Any questions about this one? Okay. I'll just do one more polynomial example, and then I promise we'll move on to something other than polynomials. I think this was example 4. Okay. So we'll do it one more time for this polynomial function. Okay. All right, so this one maybe looks more complicated at first glance. Okay. Domain is still all real numbers though for any polynomial. Okay. Let's take a look at where this function will be equal to 0. Okay. So again, you usually want to try to factor if possible. Of course, we saw if it's not possible to factor, you would maybe try the quadratic formula if you had a quadratic equation. But here, if we wanted to try and factor this, what should we do to factor this guy? What's the first step? Factor out x minus 3, yeah. So each term has an x minus 3. So therefore, we can factor out an x minus 3 from every term. Is there maybe something else we could factor out as well, in addition to the x minus 3? Yeah, each term has a multiple of 2 in it, so you can also factor out a 2 from each of them as well, okay? So that's probably a good idea to do that as well. So factor out a 2 and an x minus 3. Okay, so what do we have remaining? We factored out the 2 and the x minus 3, so we have an x remaining in the first term. So we'll have a 2 and x, and we'll have 1 x minus 3 remaining in the second term. Sorry, let me try to, okay. And then this last term, we'll have a 2 remaining in this last one. Okay. Okay, so then we'll want to, simplify the this expression in the brackets a little bit. So if we distribute the 2x, that's 2x squared minus 6x minus 6x. Okay, but plus x. So actually, let's make that minus 5x. And then we had a plus 2. Okay. All right, so then to continue trying to solve for x, we now want to factor this quadratic. Okay. So this one works a little bit differently from the previous examples because the coefficient of x squared is a 2 now. So that maybe makes the factoring a little bit more involved. So in order to factor this, there's many different ways of doing that. I've seen students drawing like a box and doing some stuff, or drawing like an X and doing random things to get the solution. I never learned any of those. I always just kind of like looked at it and just kind of like by like guessing and checking sort of is usually how I would factor. So there's kind of a way of like a standard technique that you can apply to try to factor such a polynomial though. So I thought I would at least kind of explain how that technique worked, and then I know many of you have your own method of doing this though, and as long as your method works and you're good with it, you're perfectly fine to use your method, okay? But let's consider how would we factor this polynomial. So what I'm going to do is I'm going to do a couple things. I'm going to start by taking the first and the last number, and I'm just going to multiply them together. Okay. All right. So I multiplied the first and the last number, and then what I want to do is I want to find two numbers that will multiply to be 4, but they need to add to be the middle number, -5, okay? So if we think about that a little bit, the numbers that we'd want are -1 and -4, okay? So these multiply to be, oh, 1 second. Okay, sorry about that. So these multiply to be -4, but when you add them, they give you the middle number of -5, okay? So then once you find those two numbers, what you do is minus 5x in the middle, we're going to rewrite that as minus 1x minus 4x. And then we have plus 2. Okay. Okay. So that's still minus 5x in the middle, so it's the same polynomial. And then what you're going to do is you're going to factor this by grouping, okay? So maybe I'll write it like that to make it more transparent. Okay. So then here, in the first term, you can factor out an x. That will leave us with 2x minus 1. And then in the second term, well, we could factor out, so I wanted to factor out a -2, and that's why I kind of wrote it like this to make it easier to see. So if we factor out the minus and the 2, that will leave us with 2x minus 1, okay? And so the idea is when you try to factor by grouping, you should, after doing that, have the same expression in both terms like this. So now we can factor out the 2x minus 1 from both terms. And then that leaves us with x minus 2. Okay. All right. So I'm going to take this result from factoring this polynomial. Okay. And then now that we have the polynomial fully factored out like this, we can then see the solutions for x equals 3. X equals 2 from that one. And then this one will give you x equals 1/2. Okay. And then just in case you don't see that right away, if you set this equal to 0 and solve for x, add 1, divide by 2. So that's how we get x equals 1/2 for the third value. Okay. So then the last thing we'll do is make our sign chart. Okay, so we have 1/2, 2, and 3. Okay. And then we'll pick a test point again in each of these intervals. Okay. And then we'll plug each of these test points into f of x. And again, using the factored form of f is going to be a little bit more convenient. So I'll do this last part somewhat quickly. So we plug in 0 for x, it'll be negative, negative, negative. Okay. Plug in 1 for x, negative, positive, negative. So it's positive overall. Plug in 2.5, negative, positive, positive. And then plug in 4, and everything should be positive now. Okay. So then finally, we can answer where the function was positive and negative. So this function would have been positive in the interval 1/2 to 2, as well as in the interval 3 to infinity. And it would have been negative from -infinity to 1/2. And then also in the interval 2 to 3, okay? All right, so any questions about that one? All right, so it has been a little bit over an hour now, so I think maybe this is a good place to take our first break. So let's maybe take like a quick 5-minute break, and then we'll come back and do some more examples, okay? Okay, so I guess we can go ahead and continue. Okay. So then I'm going to move on from working with polynomial functions, and I'm going to take a look at some rational functions next. Okay. And we're going to do the same thing that we did before, where we're going to find the domain, whether it's equal to 0, where it's positive, and where it's negative. For rational functions, the domain is not always going to be, odd row numbers, so we'll need to be a little bit more careful with that one. I'm also going to add a little bit more to this. So with rational functions, there's also kind of like an easy way of finding the horizontal and the vertical asymptotes. So I think I want to touch on that as well. Okay. Yeah, so I thought I would go ahead and record this, and we'll upload the recording to our YouTube channel. There you go. So that is our YouTube channel. So later today, you should find this recording uploaded to it if you want to reference it again, okay? I'll also include in the video description a link to this OneNote notebook, so you can have access to like the work that I did as well, okay? All right, and then we'll also consider the vertical asymptotes. Yeah. So let's look at the domain first. Okay, so to find the domain of a rational function, what should we do in order to figure out what the domain is? Any suggestions? Yeah, okay. So you have to be careful with rational functions because they have a denominator in them. And wherever the denominator is equal to 0, the function would be undefined. So let's look at the denominator. Let's set it equal to 0, and let's try to solve for x. Okay. Okay, so here you can factor out an x first from each term. And then we can further try to factor a little bit more. So this should factor as x plus 3 and x minus 2, right? Okay. So then there's 3 values of x that will make the denominator equal to 0. So then what would the domain of this function be? Okay, so the domain should be like all real numbers except for these places where the denominator is 0, okay? So if we wanted to write out an answer using interval notation, it might be useful to mark these places where the denominator is 0 on a number line. So we want the domain to be all real numbers except at these 3 points. So there's going to be everything from -infinity to -3. Okay. Everything from -3 to 0. Everything from 0 to 2. And also everything from 2 to infinity. Okay. All right, so then next, let's take a look at part B. Now in part B, finding where the function is equal to 0. So if we were to take the function and set it equal to 0 to try and solve for x, that might look complicated, but you can multiply both sides of this equation by the denominator. And if you multiply both sides by the denominator, you will cancel it out on the left. So we will just get x squared minus 16. Whereas on the right, since we were multiplying with 0, it would still be 0, okay? So in other words, to find where the function is 0, we really only need to look at the numerator. The denominator doesn't play that much of a role on that part, okay? So then x squared minus 16, that's a difference of squares, so we can factor that as product of conjugates, x minus 4 times x plus 4. Okay. So then we have these two zeros of the function f. X is plus or minus 4, okay? And then for parts C and parts D, let's go ahead and make a little sign chart for that. And there's going to be quite a lot going on for this one. Now, when you're making the sign chart, you want to first restrict your attention to the domain of your function, because you don't want to consider like x equals -3, 0, or 2 if your function is not defined there. So I'm going to first draw the domain of my function. And then I still want to label the zeros that we found as well. Okay. And so this time when we considered the places where the function was undefined, as well as the zeros, we have, how many intervals is this? 6 intervals total, okay? So we'll need a test point in each interval. All right. And we'll plug each of those test points into our function. Okay, now again, remember that when you're doing this part, it's usually better to use the factored form of your function. So we know the numerator factored as x minus 4 times x plus 4. The denominator, well, we factored it out over here. So it's x times x plus 3, and x minus 2. Okay. So we're going to plug our test points in, and we just need to check whether this will be positive or negative. So we plug in -5. We have a negative times a negative in the numerator over negative, negative. I think everything is negative. Okay. So then that's like 5 negatives altogether, which means that the result will ultimately be negative. Okay. And then we'll check between -4 and -3. And so we chose this test point to -3.5. And then this time you'll have a negative and a positive in the numerator. You'll still have 3 negatives in the denominator. So altogether the denominator is negative. So altogether f will be positive in that little hole there. Next test point was -1. So when we plug in -1, that's negative, that's positive. So the numerator is altogether negative. And the denominator, negative, positive, and negative, right? Negative, positive, negative. So that should be positive altogether in the denominator. So this will be negative in the f will be negative in that interval. Okay. All right. So then just a few more. So take 1 as the next test point. Plug it in for x. You get negative, positive. So altogether negative in the numerator. Positive, positive, and negative when x is 1. So altogether negative. So altogether positive. Okay. All right, we'll plug in 3. And so we plug in 3 for x. Numerator is still negative. But everything here is going to be positive now when x is 3. Okay, so that's negative altogether. And then lastly, we'll plug in 5. And if x is 5, you can kind of see everything will be positive now. Okay. That's quite a bit of work, but we found the answer for parts C and D now. So we can say that f will be positive on the 3 intervals where it's positive. So -4 to -3 is one interval. Zero to 2, it's also positive there. And then 4 to infinity. All right. And then we see that f was negative on these 3 intervals. So them out. Okay. And then I also wanted to touch on finding horizontal and vertical asymptotes for a rational function. So let's talk about the horizontal asymptotes first. So maybe first, can anyone tell me what the horizontal asymptote is just by looking at this function? Okay. So when you're working with rational functions like this, there's a rule for determining what the horizontal asymptotes are. So you can base your answer off the degree of the numerator and the degree of the denominator, okay? So let me go ahead and explain what the rule is first. Yeah, so for the horizontal asymptotes, comparing the degree of the numerator and the denominator. Here, the numerator is a degree 2 polynomial. The denominator is a degree 3 polynomial. So we have the numerator with a degree smaller than the denominator. So if the degree of the numerator is smaller than the degree of the denominator, as we have in the first example, then y equals 0 is going to be the horizontal asymptote. I'll abbreviate HA for horizontal asymptote, okay? I'll the other cases as well. So if the numerator has a higher degree, then your rational function will not have a horizontal asymptote at all. So there'll be no horizontal asymptote. And then lastly is if the numerator and the denominator have the same degree, then you have a horizontal asymptote. And the equation of the horizontal asymptote, y, will be equal to the ratio of the leading coefficients in the numerator and the denominator. Okay. And we'll do an example. So that doesn't quite make sense. It's actually really simple. And we'll see an example to illustrate what I mean by that. Okay. All right. But for this problem, the numerator has a smaller degree. So if the numerator has a smaller degree, then we have a horizontal asymptote at y equals 0 at the x-axis, okay? All right. And then lastly, for the vertical asymptotes, could anyone tell me where the vertical asymptotes of the function are? How do we determine that? Does anyone know? Okay, so I'll also give you guys sort of like a rule for how to determine where the vertical asymptotes are for a rational function. So for the vertical asymptotes, you look for where the denominator of your function is 0. There's a small caveat to this though. So you look for where the denominator is going to be 0, but you want to do this after factoring the numerator and the denominator. So look after factoring both of them. And canceling anything out that the numerator and denominator have in common. Okay. So looking at this example that we had, so this is the function with the numerator and the denominator fully factored, okay? So when you factor the numerator and denominator, if they have something in common, you'd be able to cancel something out. In this case, there's nothing to cancel out though, because there's nothing in common. So then we look at where the denominator is 0. So we know it was 0 at x equals 0, at x equals -3, and then at x equals +2. So these three vertical lines would be the vertical asymptotes of our function. Okay? All right, so we're going to do just a few more examples of rational functions. And then I'll also make some comments regarding how you might do things in your calculus class as well, okay? But let's do a couple more examples first. We'll keep all this stuff in mind. Okay, so we have another rational function here, and we're going to do the same type of question. We're going to find the domain, find where the function is 0, positive, and negative, and then we'll also talk about the horizontal and the vertical asymptotes, okay? So let's look at the domain first. So just as before, to find the domain, we want to start by finding where the denominator is 0. So factoring this, you can start by factoring out a 2 and an x from both terms. All right, and then here, x root minus 4 factors as x minus 2, x plus 2. So then that gets us 3 possibilities. So then for the domain of your function, the domain should be all real numbers except for -2, 0, and 2. Okay? So then as an interval, we would have that for the domain, okay? Or rather in the interval notation, that this would be the domain. Okay. Part B was finding where the function would be equal to 0. So to do that, we really just need to check where the numerator is 0, as we saw in the last example. Okay. And this one's maybe a little bit complicated. It's cubic. But there was a formula for a difference of cubes. You don't necessarily use this too often in your calculus class, but it might come up every once in a while. Okay. So here we had like x cubed minus 2 cubed. 2 cubed is 8. Okay. Okay, so let's remind ourselves what the difference of cubes formula was. It's a minus b times a squared plus ab, and then plus b squared. Okay. So we can use this formula to factor x cubed minus 8. Yeah. Okay, so a would be x and b would be 2. Well, actually, this is kind of silly, isn't it? Well, okay. I guess I wanted to show you guys the difference of cubes formula, but now that I think about it, if you were just solving for x, okay, so this might come in handy, so I'll leave it there anyways, but if you just want to solve for x, I guess you should just move the 8 over. So, and then you can say x would be the cube root of 8, which would just be 2. But, okay. So here we solved for where the numerator is 0, but be just a little bit when you're doing this, okay? Because you need to take into account the domain of your function. So the numerator is 0 and x is 2. But earlier we saw that 2 is actually not in the domain of your function. Okay. So then actually if 2 is not in the domain of your function, then what that really means then is that this function actually has no zeros then, okay? So it should have had a 0 at x equals 2, but it doesn't because it's actually not defined at 2. So therefore, this function has no zeros, okay? Okay. So then let's talk about where our function is positive and negative next. Okay. So we're going to start with the sign chart again. And so for the sign chart, start by writing out the domain or drawing it out. Okay. We'd also mark any zeros on the number line or on the domain after that, but this function didn't have any zeros, so all we have is these 4 intervals that make up the domain of f, okay? So we could pick a test point in each of these intervals. And then we'll want to plug these test points into our function. Okay. So we'll plug the test points in. Let's start with -3. Oops. Okay. So we plug in -3 for x. Negative minus 8 is negative altogether in the numerator. In the denominator, we'll have negative times a negative times a negative when x is -3. So it's positive first, okay? Let's plug in -1 next. So if x is -1, -1 minus 8 is negative. X is -1, negative, that'll be negative, but now this is positive when x is -1. So altogether, this is positive, so it's now negative. Okay. If we plug in 1 for x, I guess the numerator is still negative. The denominator of x is 1, positive, negative, positive. So altogether minus, so altogether plus. All right, and then lastly, if x is 3, so x is 3, 27 minus 8 is positive. And everything in the denominator is positive when x is 3. Okay. All right. So then therefore we see that f is positive on minus infinity to -2. Also positive from 0 to 2. And also positive from 2 to infinity. Yep. And then f will be negative only on this one interval from -2 to 0. Okay? Now let's talk about the horizontal and vertical asymptotes for this example. Okay. So then I guess at this point, let's talk about the horizontal asymptotes first. So I guess we'll just look at E first. So earlier I wrote out the rule for horizontal asymptotes, okay? And in my example, we have the situation where the degree of the numerator is equal to the degree of the denominator. So both numerator and denominator have degree 3, okay? So therefore, we will have a horizontal asymptote, and the equation for it will be y equals the ratio of the leading coefficients, okay? So by leading coefficients, what I mean is I'm referring to the coefficient of the highest powers of x, which would be the 1 and the 2. These would be the leading coefficients. So I want to do the ratio of the leading coefficients. That would just be 1 over 2. So then y equals 1/2 would be the equation of our horizontal asymptote, okay? Okay. And again, that's just coming from like 1 over 2. All right. Now, as for the vertical asymptotes, okay. Okay, so for the vertical asymptote, you're checking where the denominator is 0, but you have to simplify by canceling anything out that you could in the numerator and the denominator, okay? So actually, I think this is where the difference of cubes formula is kind of useful. So I would want to factor out the numerator. So therefore, I would use the difference of cubes formula for this part. So it's going to be a minus b, a squared plus a times b would be 2 times x. And then b is 2, so plus b squared would be 4. Okay. So I use the difference of cubes formula to factor the numerator. And then the denominator, I guess well, it's not a big deal. So then this is the denominator, and if we fully factor them out, we see that the x minus 2's will sort of cancel. So after the cancellation, your denominator, you can, like what's left of your denominator is 0 only at x equals 0 and x equals -2. So then x equals 0 and -2 would be the vertical asymptotes of this function. Okay. But x equals 2 would not be a horizontal, would not be a vertical asymptote because it kind of got canceled out with the x minus 2 in the numerator. Okay. Okay, so are there any questions about that? Okay. So then I'll make a comment about what you'll be doing in your calculus classes. So you should at some point this semester touch on horizontal and vertical asymptotes. When you get to that point in your calculus class, I will say that they'll want you to answer like, where does your function have a horizontal asymptote? Where does your function have any vertical asymptotes? They'll want you to answer those questions using limits, which is like something that you guys will be learning in your calculus class. So the way that we determined where the function has a horizontal and vertical asymptote, we determined that using like these rules. But in your calculus class, you won't be able to rely on these rules. You have to solve the question using limits instead. That said, that doesn't mean that this is like useless for you guys. I think it does help to have another way of solving those types of questions so that you can like maybe check your work, or maybe you'll know what the answer is ahead of time, and that will guide you in solving your question using limits and doing it the calculus way. Okay. Okay. I'll also make one other quick comment, and then I'll move on to maybe like my final topics of the review. Regarding these rules for horizontal asymptotes, there was a mnemonic that some people seem to have learned. So I don't know if you guys ever saw this before. Does this look familiar to anyone? It's a Bobo button HDC. Okay, well, this is like a mnemonic for remembering how the horizontal asymptotes work. So what this stood for, it was like bigger on the bottom. And then this is just like read as a 0. So that's referring to if the denominator has the bigger degree, then 0 is the horizontal asymptote. So that's like the Bobo part. This is the first statement there. The button was if it's bigger on top. So if the numerator has the higher degree, then there's no horizontal asymptote. So n is like no horizontal asymptote, or like nothing, no horizontal asymptote. Okay. HDC is referring to this last one. The EATS refers to exponents are the same. So in other words, they're referring to if the degree of the numerator is equal to the degree of the denominator if those exponents were the same. DC refers to divide coefficients. Just what I talked about here. You divide those leading coefficients to get your horizontal asymptote, okay? So a lot of students seem to have learned this before, so I thought I would just mention it to you guys as well. So it's Bobo, button, each DC. Okay. All right, so there's a little bit less than an hour remaining. I think I'm gonna go ahead and there's another class of functions that I wanted to touch on before the end of this review, so I think I'll go ahead and move to that now. So I want to talk a little bit about the exponential and the logarithm functions. And in particular, I want to focus attention on e to the x and also the natural log function in particular, okay? So first, it's generally going to be useful to have a rough sketch in mind for what the graphs of these two functions look like. So I'll go ahead and draw just a quick picture of each of them. So y equals e to the x will look something like this. Maybe I'll try to draw that a little bit better. Okay. And when x is 0, y is going to be equal to 1 because e to the 0, or remember that any non-zero number raised to a power of 0 is considered to be equal to 1. Okay, so e to the 0 is 1, so that's why it passes through that point. The natural log function, its graph looks something like this. Okay. Okay. And the natural log function, it passes through the point 1, 0 there. Okay. So in other words, natural log of 1 would be equal to 0. So that's something that's useful to know. Okay. And these two functions, they are related to each other. Who can tell me how these two functions are related? Does anyone know? Yeah, these two functions are inverses of each other, okay? Okay, so let's kind of look at some more of the properties of E and ln, and we can kind of like see like why some of those properties may be true because they are inverses of each other. Let's start by looking at the domain and the range of each of these functions, okay? So what's the domain of e to the x? So if you look at the graph, there's no place where it's going to be undefined. So the domain is going to be all real numbers. Okay. We haven't talked about it today, but I imagine you guys probably know what the range refers to. What is the range of e to the x? Based off its graph, what would you say the range is? Yeah, okay. So the range refers to like all the y values of the graph. So the graph is always above the x-axis, so it's like strictly positive always, okay? All right, no problem. And something that's kind of like worth emphasizing in particular about this is e to the x will never be equal to 0. So no matter what you plug into the exponent, e to any power can never be 0. And that is often something that kind of comes up when you're solving problems that involve e, okay? Let's look at the natural log function real quick. So if you look at the graph of the natural log function, this time the domain is not all real numbers. You'll notice that natural log is not defined when x is negative. You'll also notice it's not defined when x is 0, okay? So the range is really, sorry, not the range, the domain is really all positive numbers. Okay, so ln is only defined when x is positive. Okay. Now the range of the natural log function though, so you can see if you focus on the y values of the graph, the y values, they do go all the way down to negative infinity. And they do go up to positive infinity. So the graph is not like cut off at any point above. It doesn't have any horizontal asymptote like that. But it is pretty slow as it like increases. Like it increases very slowly, okay? So in contrast, the exponential increases very quickly, okay? All right. And so I guess these results for the natural log function should be expected. Since these are inverse functions, their domain and range should be like swapped. Okay. So you can see that that is indeed the case, as it should be for inverse functions. Okay. All right. Now, I'll mention a couple of properties of each of these functions. So for E, really, the exponential function has all the usual properties of like how exponents behave, if you will. So e to the x plus y is just going to be e to the x times e to the y. That was just like one of the properties of how like exponents work. If you have something like e to the x times y, that's the same as like e to the x and then all raised to the y. And it's also the same as like e to the y and then all raised to the x. So, yeah. As a reminder of how negative exponents work, remember if you have a negative exponent, that means that you can move your expression to the denominator with the exponent becoming positive when you move it down, okay? Okay. Natural log also has some interesting properties to it. The properties of natural log are maybe a little bit more interesting and useful, perhaps. Okay. Okay, so one of the properties is that when you have natural log of a product, you can split that as a sum of natural logs of each factor. Okay. There's a similar property for quotients, where you can split it up as a difference of natural logs instead. There's also a property for when you have natural log of something being raised to a power. Here, you can take the power and bring it out to the front as a coefficient. Okay. And then lastly, because the exponential and natural log functions are inverses of each other, there's also this property that e to the power of a natural log, in a situation like this, the e and the ln will sort of cancel and just give you x. Likewise, if you do natural log of e to a power, that again, the ln and the e cancel each other out because they're inverses and just leave you with x, okay? So those are like some other properties, these two in particular relating e and ln to each other. So then with a brief kind of summary of some of the properties of e and ln, I'll just end the review by doing a couple problems involving the two types of functions, okay? So let's consider this first example. Now again, we're just kind of doing the same old thing. So, find the domain and then figure out where it's 0, positive, and negative, all right? So let's see how that might work for a problem like this. Okay, so for the domain, first of all, okay, so this is where you need to know like properties of the exponential function. So as we saw earlier, the domain of the exponential function is all real numbers, okay? So you can stick any number into the exponent, and e to that power will be defined. Okay. So there's no issue with the function being undefined in terms of the presence of the exponentials here. And then after that, you just have the powers of x, which also don't give you any places where it might be undefined. So the domain of this function would actually just be all real numbers, okay? So next, if we think about where is this function equal to 0? So just as before, your usual strategy for solving this is to try and factor, okay? So for a problem like this, you'll want to try and factor out what all the terms have in common, because you can see they do have quite a bit in common. We could factor out the e to the 5x from every term. Notice we can also factor out an x from every term as well, because every term has at least one x in it. So we factor out an x, and an e to the 5x will have x squared plus 2x. We factored all of this out, so there's still a plus 1 remaining though. And then we set that equal to 0, okay? We can further factor this a little bit more. So how would x squared plus 2x plus 1 factor? Yeah, it's a perfect square, so it's x plus 1 times x plus 1, okay? So now that we've fully factored our function, we see that x equals 0 will give one solution. X equals -1 is another solution. Okay. So we have 2 zeros from these two terms. What about the e to the 5x? Does that term contribute a 0 as well? And if so, what would that 0 be? Yeah, so this is where it's important to know that e to any power will never be equal to 0. So therefore, the e to the 5x does not contribute any more solutions, okay? So really, we just have x equals 0 and -1 as the only two zeros of our function. Good. So then finally, let's make our sign chart for parts C and D. So we just have -1 and 0. Okay. So let's pick some test points. Okay. And we'll want to plug them into our function. Okay, so if we plug -2 into the function, Okay, so then, of course, x would be negative. If you plug -2 into the exponential, so remember that e to any power is actually always positive, right? Okay. So it really doesn't matter what point we plug in here, this exponential term is always going to be positive, okay? And I guess this is positive because it's going to be squared. So the function will start out negative. Okay. So if we plug -1/2 in for x, so x is negative. Exponential is always positive, and anything squared is going to turn out positive as well, like that. So it's negative again. All right, and then lastly, if we plug in 1 for x, so now everything is positive. Okay. So therefore, f will be positive on just the interval from 0 to infinity. And then we see it's negative on the intervals -infinity to -1, as well as -1 to 0. Okay? All right, good. So for a problem like this, it's important to know that like e to any power is always positive, never 0. Okay? All right, let's do a couple more examples to round it out. Let's look at an example involving natural log next. This one's a little bit trickier maybe, but we'll go ahead and work it out. Okay. And we're going to do the same things. We want to find the domain where the function is positive, where the function is negative. Yeah, and 0, I guess. Okay, so let's look at what the domain of this function would be. It's not so straightforward, okay? So we'll need to know a little bit about the natural log function. Where is natural log defined, okay? So we saw that earlier at the start of this section. The natural log function is only defined whenever the argument of it is positive, okay? So natural log to be defined, whatever's inside the parentheses has to be positive. So what that means over here is this function will only be defined when, okay, so we know the inside of the natural log has to be positive to be defined. So what we need to do is figure out where this polynomial is positive in order to get the domain of our function, okay? So then if we want to know where is a polynomial positive, well, we've been doing that this whole day, right? So we can start by finding where the polynomial has its zeros. And so I'll factor this polynomial, set it equal to 0. This one's pretty easy to factor because it basically has to be 2x and x to get 2x squared. And it has to be like pretty much 1 and 1, I guess, to get the 1. You could also do -1 and -1, but that will give you a minus in the middle. So, okay. And then here, we have 2 places where it's equal to 0. If x is -1/2, that's 1, 0. And then if x is -1, another 0 of the polynomial. Okay. So then if I make a quick sign chart for the polynomial here. Oh, those are kind of close. Okay. That's not a problem though. Okay. So then we pick 3 test points, -2, -3/4, 0. Those will work. And we can plug them into this polynomial to figure out if it's positive or negative, okay? So plug -2 into here for x, and here. Both terms will be negative, so the polynomial is positive in this interval. If you plug in -3/4, it's going to be -1.5 plus 1 is still negative. It's positive, so now it's negative. And then x is 0, it's all positive. Okay. So what we see from this sign chart is that, so this polynomial is positive on the interval from -infinity to -1. And it's also positive on the interval -1/2 to infinity. So then for these, for values of x in this set, that's where f of x would be defined. So then this was going to be the domain of our function, okay? Okay. So then that was a little bit tricky. So we needed to know that natural log is only defined whenever the inside expression is positive. And then to find where this polynomial is positive, we did our little sign chart to figure that out, okay? All right. So let's take a look next at where is the function f of x equal to 0. Okay, so we've got this equation with the natural log in it. So how are we going to solve for x in this equation? There's a couple of ways of thinking about it. Okay, and why do you suggest that? That is correct. So why do you suggest that though? Yeah, okay. So this is one way to think about it. So let me scroll up and kind of talk about this. So the idea was looking at the graph. Natural log is going to be 0 when it's evaluated at 1. So natural log of 1 is 0, and 1 is the only value that will give you 0. Okay? So therefore, in order for this to be 0, we know that natural log is only 0 when the inside is equal to 1. So that would give you 2x squared plus 3x plus 1 has to equal 1 for this to work. Okay? Sometimes it's useful to think of a problem in more than one way, so I do want to suggest another way that you could have figured this out by like thinking of it differently. Okay. So another thing you might have been thinking of when you were presented with this equation is, well, it looks complicated with the presence of the natural log there. So one thing you might try to do is you might try to get rid of the natural log. So how would you get rid of the natural log? Well, that's where the inverse relationships between the exponential and the natural log will come into play, okay? So if you want to get rid of a natural log, you need to apply an exponential to it. Or to get rid of an exponential, you can apply a natural log to it, okay? So another way you could have thought about this here is get rid of the natural log, we could exponentiate both sides of the equation. So this is kind of similar to like, multiplying both sides by a number or adding something to both sides, but you're applying the exponential function to both sides instead. So if you did that, what would have happened is the e and the ln would have canceled. So it would have just left you with this polynomial. On the right-hand side, e to the 0 is 1, okay? So that's like two ways you could have thought about how to approach solving this equation. I wanted to illustrate this method as this way of thinking about it as well, just to highlight the property of e and ln canceling each other out, okay? Now from here, you can cancel out the ones from both sides. And then I guess you can factor this. And then solve for x, okay? Okay, now, when you're solving for the zeros, you do want to pay attention to your domain. Just make sure that the two values that you solved for are in the domain, right? So if I draw a picture of the domain, so it's minus infinity to minus 1. And then there's a little gap in the domain, and then it's minus 1/2 to infinity. So x equals negative 3/2. That's to the left of negative 1. But notice that x equals 0. One of the values that we solved for is it's actually outside of the domain. Okay. So then that means we would need to like reject x equals 0 as being a 0 of f because it's not even in the domain. So x equals negative 3/2 would have been the only 0 of the function. Okay. Okay. So then lastly, we want to make our sign chart to figure out where our function will be positive or negative. And I guess we kind of have a number line set up already there, but just to make it look a little bit nicer, I'll redraw it. Okay. So then we would kind of pick a test point in each of these intervals. Oh, okay. -1, -1.5. We'll do -1.25, something in between them. And then we can do 0 over here. Okay. Okay. So this is for parts C and D. All right, so let me write out what the function was over here so we can more easily reference. And I know we factored the polynomial earlier over here. It might be useful to use the factored version of the polynomial there. Okay. Okay, now because it's a natural log, it's maybe hard to know what the numbers are when you plug them in. If you have a calculator, then that's not really a big deal, right? You can plug -2 in for x, use your calculator to figure out what the natural log of all that stuff on the inside is to determine if it's positive or negative. But let's say you want to do this without a calculator. So how could we do this? We can reference or we can use some of our knowledge of the natural log function to figure this out without the need of a calculator. So we know that natural log is 0 when it's evaluated at 1. It'll be positive when you evaluate at something larger than 1. And it'll be negative when you evaluate it at something that's smaller than 1, okay? So that can help us here in knowing if f is going to be positive or negative. Okay, so let's plug our test points into here, okay? And let's see what do we get when we do that. So if I plug -2 into here, this would be -3 times -1. So it'd be +3. Okay. So 3 is larger than 1. So natural log of 3 should be positive. Okay, so that's a positive number. If I plug -5/4 into here, so times 2 is -5/2. I'm going to add 1. I'm going to times -5/4 plus 1. That's -3/2 times -1/4. So it's 3/8. So 3/8 is between 0 and 1. So natural log of 3/8 should be negative. Okay. And finally, if you plug in 0 for x, oh, wait a second, did I mess up there? Oh man, okay. Why didn't anyone tell me earlier? All right. 0 is to the right of -1/2. I guess I was thinking of this as being +1/2, so I marked it to the left, but no, that's my bad. 0 is on the right. That's my bad. Okay, so first, x = 0 is in the domain. So let's fix that real quick. So then I need to, oh, dang it, adjust by including 0 here in my sign chart. All right, so then that means I can't choose 0 as a test point. So something between 0 and -1/2, -1/4. And then we can choose 1 for the last value. Okay. Cool. All right, so then let's see here, x, we're going to plug in -1/4 for the next test point then. So if x is -1/4, that's 3/4. -1/2 plus 1 is 1/2. Is that, oh, it's 3/8 again. Okay. So when x is -1/4, it looks like you'll get natural log of 3/8. And then we know that that's negative because 3/8 is between 0 and 1, okay? And then we'll plug in x = 1 as the final test point. If x is 1, you're just going to get natural log of 3 times 2 is 6. And that's going to be positive because 6 is larger than 1. So natural log of 6 should be positive, okay? All right. So finally, we can say that f is positive on the interval from -infinity to -3/2. It's also positive from 0 to infinity. And then it'll be negative from between -3/2 and -1. It's also negative between -1/2 and 0, okay? All right. That was quite a bit, so I guess, are there any questions about any of that? All right, no problem. I'll do one quick example. This is, I guess, the only example that's not actually doing a sign chart. That's, and then we'll end it with this, okay? Probably some of you, hopefully all of you have seen problems like this before. We have a pretty complicated expression with natural log. And what we want to do is simplify this using some of those properties of natural log that I mentioned at the very start, okay? So we'll do this pretty quickly and then I'll let you guys go. I'll copy the properties down below for reference. Okay. So when you have a really nasty expression in your natural log, it'll probably be good to break it apart into a bunch of like natural logs using these various properties, okay? So what I'll start with in this example is, okay, so in the numerator we have, you can think of it as having three things multiplying together, 3 x minus 3 squared exponential. And then you also have two terms that are multiplying in the denominator, okay? So when you're splitting this apart, you can use the first two properties to separate it into, here we're going to separate it into 5 different natural logs. So you can split this as natural log of 3. So starting with the numerator, you can do natural log of 3 plus natural log of x minus 3 squared, and plus natural log of the exponential. Now for the two terms that are lying in the denominator, for terms in the denominator, those are going to be subtracted according to this second rule here. So you can split this as like minus, and then you got natural log of x squared, and then another minus natural log of this fifth root. Okay. Okay. Now after that you have no, maybe it would have been better if I won't worry about that. So when you have a power on the inside, you can bring the power out to the front. So we can apply that to a couple of these terms, okay? We also had the inverse relationship between natural log and e. Natural log of e to a power, the ln and the e will sort of cancel and just leave you with the exponent. So let's see how we can apply those rules to what we have here. So this will give us natural log of 3. Here you can bring the 2 out to the front to get 2 natural log of x minus 3. Now for this term here, that's ln with an exponential. So the ln and the e would sort of cancel. It leaves us with 2 minus x to the 6th, whatever was in the exponent, okay? For this term, you can bring the 2 out to the front. Okay. And then for this term over here, remember that raising something to or something being fifth rooted. Fifth root is the same as like raising something to the power of 1 over 5, okay? So therefore, once you rewrite it as a power of 1/5, you can bring that 1/5 out to the front. Like that, okay? And then at this point, there's not that much else you could do. So I think this would probably be a good enough place to leave it for like the final answer. Okay. Okay, so then I'll go ahead and end the